Hello, welcome back to Stat 3050. We're online still, but just having a good time. This is gonna be almost it. We are almost at the end. I just have one more sort of way of transforming data that I want to show you, and then after that, we're gonna move into some more or less kind of secondary methods that are a little bit not beyond this class, but not taught elsewhere at the University of Wyoming. So I would like to go over that in a future video, in the next video, I guess. But for right now, we are doing categorical times numeric interactions. What is that? Well, I'll show you. So per usual, 3 goals, well, 2 goals. Introducing this concept, and then writing out regression equations. So in this instance, it is kind of necessary to sit down and write out the regression equation to kind of see what's going on, because, well, you'll see here in a second. That is it. This is just one concept in this video, but it's a pretty important concept, so it's important that we sort of get it all figured out and straightened out. And then again, per usual, times 2. This example is brought to you by beats that are just too chill. Oh boy, I'm listening right now. You can't hear, but I'm listening to Limes here on the right. Sorry, here on the left is Limes. Very, very nice. And then sort of on the opposite end, one of the better albums I think of the 2000s. Well, I guess 2010s is Bon Iver's 22 a Million. So good. Super good. It's a different kind of chill. Maybe it's like even unchill. But it is super good. So check it out. Limes, if you're trying to chill. Bon Iver if you're trying to chill, but in maybe a different kind of way. Okay, let's get into it. So I have I've written a bunch of code already. So one, we can save time because we're pretty far into the semester that you should have an idea of how to make all of these plots and models and everything. So you're not going to see me type everything out. If you're curious, the code is online. So you should be doing that side by side. So today we're working with a data set regarding the pincher force, height, and 3 different species of crabs. Okay, so we'll read that in. I've already got my working directory set and everything. So let's take a look at it, and we see that, well, we've got force, height, and then species. Okay, so force is the pincher force, how hard the crab can pinch, I suppose. That's a continuous variable. Not too sure the units. Again, doesn't really matter for this class, at least. This is not a biology class or a crab biology class. Statistics. Anyway, so then we also have the height, also continuous. It is, let's see, yeah. Continuous, not rounded, so it's not rounded to 0.5 or to the next whole number. It is fairly precise. And then we have 3 different species here. Species A, species B, and species C. Okay, and so the goal of this, of these data, is to figure out how both of these are related to force. We're going to kind of step away from the idea of prediction just for now. Oftentimes in statistics, we really only care about relation rather than relation and prediction, but important to know the relevant criteria for both of those. But we're just going to be looking at how these 2 variables, height and the species, are related to force. Okay, so the first thing that we always want to do is we always want to plot the data. And in fact, another thing, we'll just check the old structure of the data. I'll write that out to make sure it's all being treated appropriately, and it is. Force is numeric, height is numeric, and then we see that the species is a factor with 3 levels. And it looks to me like the the reference level is species A here. Important. We could change that if we wanted, but just good to note. Okay. Sorry, didn't mean to clap. Let's plot this data as a scatter plot, just to see how it's behaving generally. Okay. And we see that as height increases, force also increases. We also see, oh no, get out of here. Sorry. We also see that the model here, in general, is going to be doing a fairly decent job around here, around the smaller values. But as you go further out, the points kind of spread out and are a little bit more uncertain. Right? The line is not doing a super great job of sort of defining those points out there. That's okay. That's okay, because we're not looking at the residuals yet, because we have not included the 3 species. We're only looking at this from like a general point of view. Okay, so let's include the 3 species. So we do that by just saying color equals species. In here, I put it in the geom point, so it's going to color the dots. Actually, I'll just show you rather than tell you. But we'll see that it only colors the dots, and I also switched up the line just a little bit. So we see here that there's a fairly big difference between species A, B, and C, especially species A, right? We see that species A and the red dots are pretty much only below the regression line. And they have a fairly similar height to the rest of the species, but the force, it's not the same, right? We have ways of modeling that, and we will here in a second. And then we see that B and C are both fairly similar. We haven't looked at the slopes of the 3 species yet, but let's do that now. So we run that. Okay, so this is a little bit kind of hectic, but in fact, we'll leave it for now, because the next chunk of code will get rid of the general trend. But we see here that species A and B, the green and the blue line, follows the general trend pretty well. We see that species B has a bit of a steeper slope than the general trend and species C, but for the most part, they're both sort of increasing, right? They both have a positive relationship. Species A, though, that's a bit odd, right? We see that line for species A is pretty flat. There's almost no relationship between height and force for species A. Now, if we were to just take out species A and model it that way, the trend might look a little different because we won't have species B and species C. But still, comparatively, we kind of need to keep it in the model because that's the data that we have. We see that if we were to model this just by itself, as far as the general trend, so ignoring the species, we'd be losing a lot of the story. A lot of the picture would be gone, right? Okay, so let me run that next plot here. Yeah. So same thing. I just got rid of the general trend there. Species A, barely any relationship between height and force, and then species B and C are pretty similar to each other, but still a bit different here and there. Okay. Again, let's take a look. I'm going to make a box plot here of the species and their heights. Because from here, we can say that the heights of the species are all pretty similar. They're all pretty close. And we see that here. Cool. So the crab height is, let me do this too. Whoa. Sorry. Good Lord. Okay. So anyway, we see that the crab height here is all pretty similar. As far as the medians go, species A and species B, pretty much right around the same value. We could pull up the summary statistics if we wanted. Species C being a little bit taller than the rest. But the range for all of these species is about the same. We see that these two outliers here in species A sort of kind of encompass the other two species, but for now, this is fine. This is fine to report. But if we were to look at the other end, if we were to look at species and the force, we would see that species A is, gosh, it's my sister. Species A is pretty small, right? And then compared to species B has a really wide range of data. And then species C, same kind of deal. It's a little bit more clumped up, more or less. But the biggest thing here is that species A is the one that is fairly significantly smaller, or weaker, we would say, than the other two. Significantly as in noticeably, rather than statistically, because we don't know yet. Okay, so let's go back over to the code, and let's see what is going on. So the first thing we could do, it would be incorrect to do, and I've got that sort of noted here, is just modeling force as a function of height and leaving out the species, okay? Totally ignoring species. So we do that. Let's look at the residuals first. I'll just pull up the summary statistics. I'm trying to keep everything on the same page here, just for organization. Okay. Let me get the cursor out. Let's look at the residuals first over here on the right, and then we'll look at the coefficient table. We see that when we leave the species out, the residuals don't look too bad. They are sort of fanning outward. It's kind of hard to tell because for whatever reason, the number kind of covers up the point here, so it's a little harder to see the pattern. But that's okay. We do see that there is a bit of a pattern there, in that it's fanning outward, okay, and it's sort of clumped up over here too towards the smaller values, but this is not great, right? We would be kind of questionable about the second assumption here of equal scatter. Okay, so it all fits around a line fairly decently, but it's the next step of, is there a pattern? Is there equal scatter? There is a bit of a pattern, and there really isn't equal scatter. So I would go ahead and say this is not the best. This is not the best model. So let's look at the coefficient table, and we see that even though our p-values here are both significant, right? They're both below 0.05. The residuals don't look great, right? They're not too bad, but we know that they could be better because we have not included the species yet. We're ignoring that, and which in this case is wrong, right? We don't want to leave out the species. Another thing to note here too is that with this one predictor here, just height, the R squared is, it's not high, it's not great. The adjusted R squared is 0.38. That's okay. That's not the best. It's not the best. Of course, I don't give you, values that indicate high R squared or low R squared or whatever. But in this case, good to keep in mind that with just this one predictor, it's not stellar. Okay, so let's include the species. We'll know that that's going to be more of the story that's being told, right? We're going to get more of the picture. The second thing is that we're supposed to include the species because that's what we're told to do. Not me telling you, but maybe a researcher comes up to us and asks us to include both. That's our job, right? We want to make sure that we're being as consistent and being as statistically responsible as possible. Okay, so and the third thing, we know that when we add a new predictor in, the R squared is going to go up. Okay, by how much? Well, we don't know. So let's go ahead and do that. We'll make model 2 here. Model 2 includes height and species. Run the residuals, look at the summary. Great. Now, already, let's look at that R squared. Don't even look at the residuals yet. Ignore that. The R squared has gone up significantly, right? It's gone up it's essentially doubled, right? It was at like 0.35 earlier, now it's at 0.65. It's pretty good. Pretty good. Okay, now let's look over at the residuals. Uh-oh. Who cares about the r squared? Because the residuals look like trash. We see that there's a bit of curvature going downward, a bit of downward curvature, and it's also kind of fanning outward as you go, as you increase the fitted values, right? So the further out you go on the line, they start to spread out quite a bit more, which we saw in that original scatter plot. So that's not great. Another thing to notice, too, is that all of the p-values are statistically significant. Just because all of the p-values look great and the r-squared went way up doesn't mean that it's a good model. In this case, the residuals tell us that, hey, it's not great, right? It is not great. So our first step when we have residuals that look like this is to log transform something, right? I don't think there's enough evidence to do a quadratic regression for this. We didn't really see a lot of curvature. Plus, that would get so confusing to interpret, especially when we have the species variable too. So we won't consider that. You could if you wanted, but not totally. We don't have enough evidence to say to say that. So let's log transform y and see what happens. So we've got log force now as a function of height and species. Run all that. See what we get. Okay. Now, over to the residuals versus fit. It's looking a little bit more spread out, but now the fanning is kind of going inward now as you go further out on the fitted values. That's not great. Okay, that is not good. That's something that we cannot live with in that case. We're going to be doing a quote-unquote sort of better job at the higher values now with the model than we would be with the lower models. We want that error to be consistent throughout. We don't want it to be sort of uneven depending on where you are in the regression equation. We come back over to the coefficient table, even though it doesn't really matter because the residuals look bad. We see that we've lost the intercept. Again, we don't care about the intercept because we don't want to predict. We just want to relate. So we only look at the p-values for the slope coefficients, not the intercept as well. P-value, not the p-value, the r-squared has stayed about the same. Again, we don't care because the residuals look bad. Always look at the residuals first before you make any interpretation or judgment on your model. Always look at the residuals first. Okay, so, sorry, I clapped again. Trying to keep your attention. We're going to log x now. We've logged y. Didn't look great, so we'll try the other way. We'll try logging x. So we'll run that. Okay, here we are. And what did we see? Well, we see about the same residuals as we saw without log transforming anything. We have that sort of downward curvature and it's fanning outward. Not super good. All the p-values are statistically significant. Who gives a rip? We don't, because the residuals, again, look like trash. Okay, so let's try log transforming x and y. What did we get? Bad. Again, right? The residuals kind of have that fanning back inward now that we don't want. That's not good, right? All the p-values are statistically significant. We don't care. We don't care. This is not a good model, right? Always look at the residuals. You're going to hear me say that all the time. Oh, okay, there it is. Well, we've exhausted all of the transformations that we've learned about in this class so far, right? We've tried log transforming x, we've tried log transforming y. Not enough evidence to do a quadratic term, especially with the species variable being in there, kind of difficult. What do we do? Okay, so recall that when we had categorical predictors, we assumed that the slope was the same. but the y-intercept was the thing that changed a little bit. Okay, that's what we were doing when we just had categorical and then some continuous variable or some continuous variables, right? We assumed that the slope was about the same. When we plotted it in the last example with categorical predictors, we saw that the lines for each of the variables, when we split it up that way, we saw that they both increased in about the same sort of way with slightly smaller intercepts, or slightly different intercepts, we'll say. That's fine. However, we saw here, and let me pull it back up too. Let's see. Yeah, it's this one. Kind of hard to tell when you're not zooming in. Okay. So what we saw here was that species A has a way different intercept and a way different slope than species B and C. Species B has a way different intercept and a fairly different slope compared to species A, and the same thing with species C, right? They're all slightly different, especially when we're looking at the y-intercept and the slope, right? So when we modeled it the first way with the height and species, we were assuming that the slopes were the same, right? That's not right. That is 100% not right, which we see here, right? So how do we force the model to assume different slopes? Well, what we do is we say, well, there may be an interaction between our categorical variable and the continuous predictor. Okay? How do we do that? Well, we can deploy, that's a fun word, we can deploy a new type of transformation, quote unquote. It's not totally a transformation, but we're going to be adding another term into the model, okay? And based on what we saw earlier in that small little PowerPoint and what I have here is that we're going to be multiplying the categorical variable to the numeric predictor. What's that going to look like? Well, let me take a step back and give you some terms to kind of work with here. When we say that we've got, well, in day-to-day life, when we interact with something, it's more or less kind of communicating physically or verbally with something else, okay? Statistics, it's a little different. Kind of how the term significant is different in statistics as it is in real life, same thing here, right? Interaction doesn't mean that the two variables are talking to each other or interacting with each other, but what it means is that they might kind of have a relationship between themselves that we have not accounted for, but we're going to account for it now. So with that, when we have interactions, we also have the quote-unquote main effects, okay? So that is, in this case, the height and the species. Those are the main effects. And then we have the interaction, right? The sort of relationship between height and species, okay? So how do we do that? Well, you'll see here that I've got it multiplied together. That's what we're going to do. We're going to multiply species and height. And what that's going to do is it's going to sort of define, it's going to include that behavior between height and species, okay? So all we do is this. Whoa, not that. We do this, okay? So we just do, we don't have to use any I operator. We don't have to do anything like that. We just multiply these two things together, okay? And this with the asterisk here, shift 8, if you're trying to search for it. Okay, so we have our main effects, height and species. We have our interaction, height times species, and then our data, okay? So what is that going to look like? Well, let me make that model, and then I'll run the residuals, and then I'll hit the summary here. Now, let's not even look at the coefficient table yet. Let's ignore that. And let's look at the residuals, okay? already we see that they look way better. There's no more curvature, there's no more fanning outward. There's still a bit of clumping here, but for right now, we're not going to worry about it because we know that species A by itself is already kind of way different than the other two species, right? And that's sort of what's happening here. We're going to ignore that. We could log transform the outcome if we wanted. We get pretty similar results, spoiler alert. But for right now, comparatively, this is a way better looking residual plot than the other models that we tried. Let me also run the histogram here. So our first assumption is that it fits a straight line, the data do. The second assumption is that the residuals are equally scattered. For the most part, they are. And then we want to look at the distribution of the residuals. So we'll do that. And it looks pretty decent, right? We're pretty liberal with how we look at histograms. We more or less care about the first two assumptions the most, which we see here have been met. So that's great. Okay, so let's go back to the coefficient table now. Boy, it looks a little funkier than what we're used to. We see that we have more terms than maybe we should. No, if you think about it, all we're doing is we're multiplying the different levels to height, okay? And so we know that what R is doing in the background is just coding the different levels as ones and zeros, right? So essentially what it's doing is multiplying it by, multiplying height, in this case by 0 or 1, whatever. We're not going to worry much about how R does it. We're just going to say that R does it. We're not worried about how R does it. But in this table now, we have to do a little bit more work to see how things are related to force in this case. So let's take it one term at a time. We get height species, right? Species B and species C. Those are our quote-unquote main effects, okay? And then below that, we see that we have height colon species B. That is the interaction effect between species B and height. That's height times species B, okay? And then below that, we see height times species C. Great. All that's fine. Okay. Going back to the main effects, let's look at the p-values. Oh boy. All right. So we've got height has no statistical significance to the outcome. Wait, does it? Okay. Well, so what we're saying here is that the main effect of height has no relation on the outcome. Okay, the p-value is way above 0.05. Same thing for species C. The main effect of species C has no effect in general on the outcome. Species B is a different story because it's got a p-value above of below 0.05. Right? It's 0.01 in this case. So we would say that the main effect of species B is statistically significant. Okay. The buck doesn't stop here though. In fact, when we're working with interaction terms like this, we really only care about the interaction term. We don't care about the parent components of it. We only care about the interaction term because in this case, and a lot of the cases with interaction terms, is that it's doing more of the work. It's doing more of the storytelling in this case because we've essentially included two variables into one, right? Okay. So we would say that when we account for the fact that species B is going to have a different height on average than the other two species, right? Those two variables, height and species B, they behave differently than height and species A and height and species C, okay? And we would say that when you include the fact that they behave slightly differently with each other than the other species, we see that that effect is statistically significant on the outcome. And the same thing with species C and height, right? The relationship between those two things, the way that they behave by themselves, is statistically significant in the relationship to the outcome, to the force in this case. Okay. Whoa. So that's really something, right? But what we've done here is we're saying, okay, we're forcing the model to say, hey, I think that the y-intercept is going to be different when we include species. We saw that in the plot. But also, I think that the slope is going to be different too. I want you to model that. And R says, okay, just multiply them together and we're set. And we see now that we are set. But this is where that second goal comes in. The second goal is writing out those regression equations, right? In this case, it is very handy to be decent at adding and subtracting and multiplying by 0 or 1. Thankfully, it's nothing too complicated past that. But it helps so much to write out the regression equation to see how these things actually affect the outcome. Okay, so what I've done, in fact, is I've already done that. Woof, okay, so going back a step to what we did last week with just these categorical predictors, if we only modeled it without the interaction term, this is what we would get. So we get this full model. We get this full model here, right here. Nice. That includes only the species and only the height. Remember that when we're in regression, especially in multiple regression, we say holding others constant, x affects y this way, in whatever way, okay? Which is what we're doing here. We're saying if we wanted to interpret height, this term right here, we would say more or less ignoring these two terms, height affects y by, this much or whatever. Okay. We know that's wrong, but let's go ahead and interpret it as such, right? So if we wanted to look at species A here, species A, we would just plug in 0 for the other two terms, and then we would get this regression equation. For species B, this is species B here, we would plug in a 1, and then we would do a little bit of algebra, figure out this, figure out this regression equation. Okay, clean it up. And then for species C, it's the same thing, right? You plug in 0 for anything that's not species C, leave in a 1 for species C, and then you get a new regression equation. This is without interactions. Okay, this is not correct. This is bad. This is not good. Okay, so we're still including all of the variables, but we're not including the fact that they obviously had different slopes. And we see here that the slope is the same when we don't include that interaction term. We see here that the only thing that changes is the y-intercept. And we know that that is not even close to what happened. What we need to happen, what we need to model, is the fact that the y-intercept is going to be the same. The y-intercept is going to be different, and the slope is going to be different. Okay. What we've done here is we've just said, the y-intercept is going to be different, but the slope is still the same. That's not true. We know that's not true. So let's go on. Whoa! Okay, so this is a lot, but that's okay because it turns out that the math is still the same. We're just plugging in zeros for whatever species that we care about, okay? Which, when we're working with interactions, this is something that you should always be doing. This is the only time that I think that it helps to sit down and really write out the regression equation because it will help you see how things are different when you include the interaction term with the species and whatever other predictors you're working with, okay? So this is our full model. This is what we got from the output, okay? Rounded more or less, but the full model, 3.16 times height times species, or minus species B, minus species C, plus height times species B, plus times height, blah, 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 right? All over the place. But when we're looking at it, when we're trying to say for the different species, right? Or it could be for anything. It could be for the different sexes, for different income brackets, for whatever, right? We would just do this. We would write out all the terms. And then when we're trying to figure out how things are related, we just plug in some zeros and some ones and we're set. Okay, so for species A, we're just plugging in a 0 for anything that's not species A, which turns out to be pretty much everything here. And we are left with, is this going to work? Yes. We're left with 3.16 plus 0.145. That slope it's pretty small, right? And we saw that. We saw that slope was almost 0, which in this case, 0.15, pretty close to 0, right? So this would be our regression equation for species A. Okay, not even looking at the p-values for the term, not even looking at any of that. We're just looking at it right now from the coefficient, from the estimate standpoint, okay? So then, for species B, we do the same thing, right? We plug in a 0 for species C, plug in a 1 for species B, right? So we get that this term here would go to 0. That means that this whole thing goes to 0. And then we're left over with this regression equation. Negative 17.3 plus 3.9 times height. A different y-intercept and a different slope, which we saw that species B had a fairly steep slope, right? Steeper than all the other ones, which we see here. At least it's steeper than species A. And it's also got a different y-intercept. Okay, very cool. Same story for species C down here. Hopefully you can read that. But for species C, it's the same situation, right? Plug in 0s for when it's not species C. Plug in a 1 for when it is, right? This whole thing goes to 0. This just turns into that value. Add it to the other values. We see that eventually we'll get two different height coefficients, right? Add them together, right? Like terms. Same thing with the intercept. Add them together, right? They are like terms. And then you're left over with negative 7.09 plus 2.43 times height. Different y-intercept, different slope. Booyah, right? Super cool. Super cool. And now we've got three different equations, right? And like half the work, right? What we could do is we could also divide up the data set into species A, species B, species C, right? And then model it, make three different models, go through that whole same thing again, except triple. Have to do everything again, make sure that there's no log terms that need to be in there, blah, 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 right? We've done it all in one step as far as the coding goes. Okay, let's see how this looks on a plot. Okay, we're used to seeing this. We have seen this before, right? Same deal. Species A, species C, species B, ABC, sorry. And we see now that if we were to trace, actually two things. Just as a note, this x-axis only goes to like 5. If we were to zoom it all the way out back to 0, make the origin 0, 0, these intercepts here would intersect at the value, right? So instead of tracing down is not totally the right thing in this case. But you would never really do that because biologically it doesn't mean anything. Because if height is 0, then there is no crab. Okay. Anyway. So going back to the model, going back to this plot, and going back to the new regression equations that we got, we see that it all is fairly clear, right? At least I hope so. In that, we see that there are different slopes and different intercepts for these three species when you're looking at height and force, pincher force. And we can trust these regression equations. At least we can trust the slope, right? And why can we trust the slope? Well, because the interaction effect, for both of the species, for all three of them essentially, because species A is the reference, we have a statistically significant value for that estimate, right? They're both below 0.05, and we could say that, okay, when you do the math or whatever, then the slope coefficient that you get is the relationship between height and force, right? So for species A, for every 1 unit increase in height, force will increase by 0.145. barely anything, right? And we see that here. It's still upward, more or less, but barely upward, right? It's almost zero. But we can still trust that because because the estimate for the interaction term is statistically significant. Same thing with species B, same thing with species C. We don't look at the main effects, right? But we do look at the interaction effect when we include it, okay? So, again, just to reiterate, you always look at the interaction effect. The parent terms, or the main effect, right? The main effect, it's there, you have to keep it in there, right? But you don't look at that specifically for the overall effect on X and Y, okay. So it always helps to write out, if you do choose to use an interaction term, right? But you don't have to. You could be fine with doing something else. But in this case, this is more or less sort of the right way of doing it. One, because that's what we were asked, right? Somebody came up to us and said, can you find the relationship between species, height, and force? You said, yeah, of course. But if you were doing your own research and saying, okay, maybe I'll just leave out species A and make an easier model with just species B and C, ignoring the fact that you ever even collected species A. Okay. So, with that being said, there is sort of some philosophy with statistics in that, well, by now, there's really not a lot of rules. There's a few things that we have to include, and there's a few things that we have to make sure are met as far as requirements, but then how you approach the analysis and how you approach the overall design of the study is totally up to you, right? So, in this case, I believe that when they were looking at these crab data, they were surprised, right? It was a total novel study, right? So they were looking at, I think, 3 newly discovered species within the last, 50 years or so. And they're all living in the same environment, more or less. And they found that they had no idea. So they had no idea that species A was going to be way different than species B and C. It was totally exploratory, right? In your own research, and research a lot of the time, you have a fairly decent idea of how these different grouping levels, or these different groups, are going to behave, right? We generally have a good idea that things, when in your own field, right? In your own field, things like this shouldn't usually happen. Sometimes they do, and it's okay that they do, and we can model it when it does happen. But if a research design is designed in a way that is at least relevant and not more or less exploratory, but sort of just trying to better define the relationship between a few things, whatever they may be, you'll probably find that everything moves in the same direction with about similar slopes, or you can assume that they're similar slopes. You can model them as similar slopes with slightly different x, with slightly different y intercepts. Okay, so interaction terms, very helpful, oftentimes necessary when it's something like this, when you have a species or some grouping level that is way different than the other ones, right? Okay. Now, with that, I think I said moments ago that there really are no rules in statistics. There are, some as far as regression requirements and everything like that goes. But when you're working with interactions, there are a few things that you have to keep in mind. Not rules, more or less, because not everyone follows them, but more or less just kind of helpful tips here. So, when you're working with categorical and numeric interactions, you always have to keep in the parent terms, regardless of their p-value, okay? So the parent term, if their p-value is above 0.05, statistically insignificant, then you would say something along the lines of, the main effect has no relationship on y, on the outcome, but, and then you look at the interaction terms. You would say that, in this case, the interaction term between species and height was statistically significant. And then you could go into the 3 different regression equations, getting more into how the slope changes. Sometimes you might run into a situation where only one of the interaction terms is statistically significant with the other group. In this case, we had 3 species. If we were to model it the same way that we did, and we only found that one of the species has a statistically significant interaction term, then you would just say, but the species B in height had a statistically significant interaction term while species C didn't, right? Okay, so that's fine. If the p-value is below 0.05 for the main effect, then you could say that there is a main effect between the relationship to the outcome and the interaction term looked like this, blah, blah, blah. Okay, now the biggest thing here is that a lot of the times people want to do the easiest thing, which I understand, especially in regression. When you have a data set that you're not familiar with, or you got a ton of variables and you just don't know where to start, oftentimes using the best subsets regression, so the reg subsets and then the subsets function and the leaps and the car package respectively, it's a pretty easy way, of seeing that. However, when you have an interaction term and you use the subsets function, R doesn't know that the parent term or the main effect is the main effect, right? So it's going to ignore it and just go for the best thing mathematically. It doesn't know that the interaction term and the parent term both need to be included. Okay, so that's just something to keep in mind. In this case, it was easy to do it by hand, and by hand, I mean coding, the two variables. Sometimes you might have a data set. Your final project is going to have something like this, where there's quite a bit of categorical and continuous variables. Using the subsets function makes it a little difficult to make sure that everything is included properly. There are ways that you can go in and tell the subsets function to include the interaction term with the parent term, but you could also do it by hand as far as sort of the order of selecting variables. The best way, I think, by quote-unquote hand, is to do the backward elimination, where you include all the variables and then slowly chip away at the ones that don't have statistically significant p-values. But that also means that you have to have a little bit of thought that goes into which ones you're removing, because when you remove a parent term and you have an interaction term with that parent term, you gotta kick out the interaction term too. So if that's a long-winded way of saying always include the parent term if you're using an interaction between that and something else. Okay. Now, another thing too is that log transforming a predictor and then using it in the interaction means a few things. One, kind of hard to explain. The math when you're working out the regression equation turns out to be a little difficult. Nothing that you can't do, but something that using a calculator might be a little bit more helpful, or even like Wolfram Alpha. If you're familiar with that, I'm totally fine if you use that. But also that means that if you have a logged parent term, that the interaction term also has to have that logged parent term in it. You can't have a log parent term and then can't have a log parent term and an unlogged or an untransformed term in the interaction. Okay, so if the parent term is logged, the interaction has to be logged. If the interaction is logged, the parent term has to be logged. Confusing. I would stay away from that for now, and until you get more practice with it. If you go on and take harder, quote-unquote harder, more advanced statistics classes, then you'll be dealing with that kind of stuff. But again, this class, you can try if you want, but I wouldn't for now. And then, if you're interested, and if you're working on a project or working on some data set where you've tried everything, right? You've tried all the categorical interactions you could do. You've tried all of the log transformations and whatever else, quadratic terms, blah, 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 blah. You can also do a numeric times numeric interaction. The math is still the same. In fact, it's not too difficult to do, but you really have to make sure that you're keeping track of all the things that you're making an interaction term out of, because it can get fairly sort of tangled very quickly. So if you're curious, I'm not going to go into it because there's just way too many combinations of variables that we could try. But if you're looking at, if you're trying to find some practice, you can use the body weight data set that we used a couple weeks ago for that. And you'll get some good practice that way. Oh, man. Okay, so one more thing. When we're looking at interaction terms, we oftentimes look at how the slopes are the same or different, right? In this case, we saw that species A was way different than species B and C. Okay, it almost had no relationship between height and force, right? It was super tiny. That is a good reason to include an interaction term. Sometimes when you're looking at the residuals of like your full model without the interaction term or whatever, you might see like a bow tie kind of pattern. Okay, that would be indicative of needing an interaction term, whether it be categorical and numeric or numeric and numeric. That turns out to be a little, it doesn't tell you what variables to make that interaction term out of. It just says that maybe, if you see that bow tie pattern in the residuals, so sort of fanning inward and then fanning outward again, then maybe, you need to try an interaction term somewhere, okay? So that's all right. The other thing that is a little complicated in that there's no math behind it, but oftentimes when you include an interaction, it's sort of intentional. It's not something that you're trying to correct for based on your model, but it's something that you want to include, right? So oftentimes, studies will be designed to say, okay, we're going to multiply these two variables together anyway, because we know that they're going to be different. And that's more of like a philosophical side of statistics. It's very subjective with whether or not you include it. And it can be, it can be complicated. This is why this is the last thing that we're going to be doing in this class, at least, because it can get just super tangled very quickly. But when you go into more advanced classes or when you're looking at your own research or whatever, oftentimes it might make sense to just initially make an interaction term out of two variables or whatever. Oftentimes, when you look at variables and you say that they're redundant, in that, if you were to look at the body weight data set, you have height, and then you have like leg length or something like that. Well, those two things on their own are pretty similar. They're doing a lot of the same job. They're covering a lot of the ground, okay? And so, if you were to make an interaction out of those two variables, you're more or less kind of combining the fact that they are highly related, right? I'm not going to say correlated. I'm not going to say anything like that. But you are doing a very similar job when you include both of those by themselves. If you were to multiply them together, then you're kind of covering more ground. You're accounting more or less for the fact that leg length and height are both fairly similar. They're doing similar jobs. Now, that's totally philosophical, right? That is so out there that, you can include it if you want. If it's too much, I totally get that too. The biggest thing, especially what we saw here, I'll go back one, is this situation where you've got three species or whatever, however many levels, and at least one is acting funkier than the other ones, right? So the lines don't need to be totally parallel for you to include an interaction term, but if they do look something like this, or even if they're like totally perpendicular, probably a good idea to include that interaction term. Woof. All right. Okay. So that's gonna be that for now. Nothing, too crazy after this. Let's see, let me see. My sister texted me a picture of Bubba. Let me see if I can find it. Yeah. Okay, cool. Yeah, so here it is. Look at him. It's a Snapchat from my sister. Look at him. He's wagging so fast you can't even see it. He's so happy. Okay. Anyway, so that's going to be that for this topic. You've got everything now that you need for your final project. Okay. So I'm going to make another video about the final project. I'm also going to make another video on decision tree regression and random forest regression. So that's 2 machine learning methods that I said I was going to do a whole section on. I thought that we would have more time, but since we lost a week because of the additional spring break, I'm going to make it just a super quick super quick video just to sort of introduce it to you. There's no machine learning classes here, I don't believe, at the University of Wyoming. So I'm going to try my best to give you a quick little intro into it because it's becoming very, very popular, especially in the world of data science. So those of you who are trying to get into data science, this is something that you'll use frequently. Those of you who aren't getting into data science, maybe you could check it out and maybe have a new sort of interest in it. That's okay if you don't. But also, you can use it, if you decide, on the final project as an additional method to the regression stuff. Okay. Anyway, I will see ya. I'll see you when I see ya. Take it easy. And, yeah. Say hi to Bubba if you see him around, which you probably won't because he lives in South Carolina. Okay.